So let's look at work done by varying force. See, till now, the forces that we look at, like say gravity, it's not varying. We always take the near the surface of the earth. Till now, all the problems that you have seen from past 2 3 years, wherever you have seen any kind of force related thing, energy or force or all of those, they are always constant. Okay, I mean, other than the few chapters you saw, but in general, when it comes to energy topic, till now, till from the previous grades and everything, it's always been constant. But what if it's not? It is in many cases the force exerted on the object, it can vary, and your work will have a different approach. We need to approach this problem in different manner. So we're looking at varying forces. So the basic idea is, how do you figure out the work in such cases? Work would be the sum of product of force and displacement. So summation of force times of displacement. For each force, what is the displacement? You have a look, add, find them, and then add them up. So we have say two different conceptual approach. One is step scenario and rapidly varying scenario. In step scenario, you get to see that, oh, from here to here the force is so. From here to here the force has changed and it is so. But rapidly varying, it won't be so, and we have to make use of a concept that you guys are and must be very clear with. Let's figure out one step at a time. So finding the area of a region under the curve for step scenario. So we'll understand what I'm talking about. So imagine dividing the force versus x curve into a smaller interval. The total work done for the displacement from xi to xf is approximately equal to the sum of these intervals. So I have an example actually. So figure I'll show it to you guys. So let me make the required arrangement. Okay, so yeah, let us see why is this a varying force. Quite simple actually. We have force versus displacement graph. From the point of 0 to 4, the force is constant and that value is 5 Newton. You guys agree? So from 0 to 4, we have an object experiencing a force of 5 Newton. From 4 to 6, that is changing, it's varying, it is reducing constantly. Okay, actually more than this, let me change the scenario. Let me not have this. So let me go with the first one. Sorry, it's this. What I mean is, and I'll call this as 1. Okay, now look at it, right? So from 0 to 4, the force was 5 Newton. From 4 to 6, the force is 1 Newton. A force acting on a particle varies with x, that is with the displacement as shown in the figure like this. Calculate the work done by the force as the particle moves from x is equal to 0 to x is equal to 6. So what our methodology over here is telling is, right, this very idea, work is equal to summation of force times of displacement. Let me put it over here. Here we are looking at step scenarios, right? We have steps. Work is equal to summation of fx delta x, where we are looking at xi to xf. So in our case, it would be, force will be 5 times of from 0 to 4 plus 1 time of 6 minus 4. That's your displacement 1 and 2, right? This is your first, I can categorize this as first, and this is my second displacement. And the force over here is 5 and the force over here is 1. So this is 20 and this is 22. So you can get such scenarios, and it's a very simple way to do it. This is a case 1. We have one more case, rapidly varying scenario. So when the size of the displacement approaches 0, the number of terms in the sum increases to infinity. However, we get to define values with this method. How do you do this? How do you handle such situation? Oh. Okay, so 1 minute. Don't have space over here. Okay, so let me, yeah. Now we're looking at case 2. You guys write the heading. So we have this formula, right? Sum of f of x dx, delta x, xi, xf. Now this is becoming very small. How do we represent that with? Yes, we make use of limits. And all of this put together, we can also represent this as integration. So we'll go to integration, that's it. So when I change the entire, I can change the entire representation to integration. So in this case, the work done would be integration of xi, xf, f of x dx. This is how you handle such varying cases. Okay, for example, we have over here a question. Yeah. So what is that we're looking at? A spring with spring constant k is equal to, don't worry, what is this spring constant? You don't have to worry about it. Has 100 Newton per meter, is stretched from 0 to 0.5 meters using Hooke's law. So this is the formula. Calculate the work done in stretching the spring. So let me not complicate it. So basically what we have here is xi, xf, f of x dx, right? Using this, we'll be able to solve this. I hope you guys are very thorough with limits. So we are displacing from 0 to 0.5. F of x is represented with 100x dx. 100 is constant, I can take it out. Integration of x is x squared by 2 and 0 to 0.5. And simplifying this will be some answer, so many joules. So this is how you solve it. Right, guys? So what else do we need to learn? So this is how you can handle work done. Where is it? Work done by varying forces. So in both the concept, I didn't make it very clear with the second case. We are finding the area, right? So F into, I'll go to this diagram. Force into displacement. So it is giving me the width and the height in each case. Width into height is nothing but the area under the curve, right? Area under the curve, you guys have studied before also. So this will give me the work. And here the diagram will be, say, something like this. Right? Say force is like that and it's varying and varying. It can be anything like this, This is F and that's the displacement, and the work done will be area under this. That's the work done. Okay. So one last thing. What if there are many forces acting on a system, right? It's not just one force, there are many forces. How do you find the work of all of this? Well, if more than one force acts on a system, the system can be modeled as a particle. The total force done on the system is just the work done by the net force. So you don't bother with anything. You find the net force of all the forces. Look at the displacement and you're done. if we express the net force in the x direction as f of fx, the total work or the net work done as the particle moves from xi to xf is okay. That will be equal to. So this is a case of many forces. What I'm writing is the mathematical expression. So the work or the net work will be equal to xi xf, the net force of all the vector sum of all the forces and your displacement. Okay, so same funda, just that you are figuring out the net force. That's it. Okay, so let me, yeah. So in this section, what we just looked at was work done by varying force. Till now, whenever we did work and energy and all of those questions, we saw forces to be constant. We didn't bother with them now. But what if we have varying forces? Well, the funda is that you figure out for every amount of force what is the displacement, multiply them individually, and then add them up. That's the funda. So we can see scenarios, step scenario and rapidly varying scenario. Of course, step scenario is just an introduction. So step scenario example is over here, right? All you have to do is divide the section into two parts. So part 1 and part 2. So I divided here into two parts, right? So this is part 1. Okay, so to the left is part 1 and to the right is part 2. Right guys? And then I figured out each work and then added them up. But it's not the only case. You can get cases wherein the force and the displacement, the force can vary rapidly, and then for such cases we have to make use of the method, and that method is your limits and derivatives. So using limits and the idea of summation, so we get integration. So we're basically using integration. So you will always have some expression expressing force in terms of displacement and stuff like that. So that you substitute and solve it and you will get the work done. Okay, so that's your right. And one last thing which I showed was, what if there are many forces? The end of it, when many forces act, it's always the net force that we take into account. So take the net force, figure out the net force, and then where did I write it? Yeah. Oh, since this is only x-axis, I need not write this. So figure out the net force and then do the same mathematical. It can be just normal step form also, or it can be as complex as this. Okay, so this will be a lot clearer as in when you do numericals. So let's start taking some small set of notes and then move on to numericals. Oh, sorry, related to this, you need to write this. And then related to this, you will need to write all of this. And then this as well. Related to this, we have this write up.